In this video, we are going to see a simulation of a Vernier caliper. This simulation is developed by Professor Mahesh Kurmi sir. So we are thankful to him for making such a nice simulation of Vernier caliper. So let's get started. So first of all, you have to enter this link of GitHub page. I will give this link in the video description. You can open there, then you will get this type of Vernier caliper. Now in case of our usual Vernier caliper, we have generally 15 centimeters. So I will take this as a 100 centimeter, say 10 centimeter, that means 100 millimeter on the main scale divisions. Then on the Vernier scale count, I will keep it as 10 only. Then zero error, I will keep it as 0 only time being. Later on we'll see how the zero error can affect the readings. Then virtual division, I will not make anything. Display values, later on we'll do these display values. Then background color we can change here. I will keep it as it is color, but if you want you can change the background color over here. Then scale we can change here, say this we can make as a 1.3, 1.4 times, whatever it may be. Say I will keep it as a 1.2 for example. So this is our Vernier caliper which we regularly use. So in case of Vernier caliper, there is a main scale. This main scale is very similar to the scale which is there in your compass box. So and there is an attached scale which we call it as a Vernier scale. So this Vernier scale is very geniusly designed. How it is designed, we will see it just in a bit. So on the main scale, if you see from 0 to 1, there are 10 divisions. So this is 0 and this is 1 centimeter. So between 0 to 1 centimeter, there are 10 divisions. It means that each division is of 0.1 centimeter, 1 millimeter, or if we are talking in terms of centimeter, then it is 0.1 centimeter. And if you see this Vernier scale, so on the Vernier scale, we have 0, 1, 2, 3, 4 and so on up to 10 divisions there. But these 10 divisions are such that the 10th division is coinciding with the 9th main scale division. It means that the 10th division is at 0.9 centimeter. So therefore, we have the main scale division as 0.1 centimeter and one Vernier scale division. Since the 10 divisions are in 0.9 centimeter, therefore one division will be 0.9 divided by 10, that is 0.09 centimeter. Now to find out the least count of this Vernier caliper, what we have to do is we have to find out the distance between one main scale division minus one Vernier scale division. So this least count will be one main scale division is 0.1 centimeter minus 0.09 centimeter is the one Vernier scale division. If you find out this difference, we will get the least count is equal to 0.01 centimeter. Now least count means minimum we can measure with the help of this particular Vernier caliper. The minimum distance or minimum dimension we can measure is 0.01 centimeter. Okay. Now the next thing we should be aware is about the zero errors actually before initially only. So for making this understanding this zero error, now if this zero error is 0, it means that your this Vernier scale 0 and the main scale 0 both are coinciding. So you can see here in this case both the zeros, that means Vernier scale 0 and main scale 0, both zeros they are coinciding. Therefore there is no zero error. So we don't have to do anything in such situation. Now if there is zero error, so then there can be two types of possibilities. One is positive zero error and next is what? Negative zero error. Now what is positive zero error? Positive zero error is whenever the Vernier scale, 0 of Vernier scale is towards the right of 0 of main scale, we call it as a positive zero error. Okay, so what is this? Say I will just write down here zero error to be say I will take it as a example. I will take it as a 5. Okay, so it is a plus 5, so it means there is a positive zero error. Now you can see here that I had made this zero error as a plus 5. Therefore what will happen, this Vernier scale 0 is towards right of the main scale 0. Now we have to find out which division is coinciding, which division of Vernier is coinciding with the main scale division. So you can see here clearly that fifth division of Vernier scale is coinciding here with the main scale. So this one you can see here, I am showing with the help of mouse. So fifth one is coinciding. Therefore in this situation the zero error will be nothing but 5 multiplied by the least count 0.01 centimeter is equal to, it will have a plus sign, 0.05 centimeter will be the zero error. So this zero error we have to subtract it from the final reading if at all there is any zero error over there. Okay, now next we will see what is called as a negative zero error. So for negative zero error, say I will take this one as say minus I will take it as a minus 5. Minus 5 we can take. Okay, or we can take it as a minus 4, for example, say minus 4. Okay, now you can see that I had taken this zero error as what, minus 4. Now since there is a minus sign over there, it means that the zero of Vernier scale is towards the left of zero of main scale. So you can clearly see here that zero of Vernier scale is towards the left of zero of Vernier scale. The zero of Vernier scale is towards the left of zero of main scale. Okay, so this you can see here in this simulation. Now to find out what will be this zero error, it's a negative zero error. What we have to do is we have to find out which line is coinciding from left side here. So 0, 1, 2, 3, 4, 5, 6. So you can clearly see that here 6 number line is coinciding here. 6 number line is coinciding. Okay, now remember, whenever we want to find out negative zero error, if you want to count in the other way, then you have to count it from right. Okay, but since we are counting it from left only, so what I am doing is I am counting from left only. So we can see here clearly that from left 6 number line is coinciding. So what will be the amount of zero error? To find out the amount of zero error, we have to find out in a bracket 10 minus the number of line which coincides. So here 6, so it will be 10 minus 6, so that is equal to 4 multiplied by the least count. So it is 0.01 centimeter, so it will be 4 multiplied by 0.01 centimeter, and since it's a negative zero error, so therefore it will be equal to minus 0.04 centimeter. Now whenever we take any reading, then if there is at all any zero error initially, then we have to subtract this zero error. Now if you subtract this zero error, then what will happen? This quantity, that is minus 0.04 centimeter, will be added in the total reading actually, because there will be minus and minus 2 times. Subtracting the negative things means it is as good as adding. Okay, so this is all about the least count and zero error. Now we will see some measurements. Before doing some measurements, I will make this clear that there is no zero error, so I will make it as a 0. Okay, so say there is no zero error. Now we'll do some measurements. So I will create some problem here. Say I will take this problem. I have to again just change this. I will make it as a 100, and this one I will make it as a 10, and this one I will keep it as a zero error as 0. Okay, so by doing this, now I will just first we will measure the internal dimensions. So yes, now if you just put it here, this display values over there, so then it will directly display these values here. So now you can see that we are doing the internal dimension measurement of this object given to us. So from here it is clear that see, this is 1 centimeter, then this will be 1.5 centimeter. After that 1.6, 1.7, 1.8 and 1.9 centimeter. So just before the zero of vernier scale, we have 1.9 centimeter line. So our main scale will be directly equal to 1.90 centimeter. And if you see which vernier scale is coinciding here, so you can easily observe here that the fifth number line is coinciding. So therefore 5 vernier scale divisions means we have to multiply it by the least count. So it will be 5 multiplied by least count, that is 0.01 centimeter. So it will be equal to 0.05 centimeter. Now we have to add these two readings, that is the main scale reading and this vernier scale reading together. So it will be 1.90 centimeter plus 0.05 centimeter. So it comes out to be equal to 1.95 centimeter. So this is the internal dimension of this object given to us. Now we will measure the external dimension of this object. So I will just keep this object over here now. Yeah. So I had kept this object over here. Now we will see what is the main scale reading. So just before the zero of vernier scale, we have 2.3. So just before the zero of vernier scale, we have 2.30. So therefore our main scale reading is 2.30 centimeter. Now which vernier division is coinciding? You can easily see that the third one is coinciding here. Therefore 3 multiplied by 0.01 centimeter is equal to 0.03 centimeter will be the reading from our vernier scale. So therefore the total reading will be 2.30 centimeter plus 0.03 centimeter, and hence the total reading, that is the external dimension of this object, will be 2.33 centimeter. Then we will find out what will be the depth of this object. So just I will take this object over here and now I will measure the depth of this object. Now see here, this is 1.5 on the main scale, and after that there is immediately there is a zero of vernier scale. So just before the zero of vernier scale we have 1.5. So therefore 1.50 is our main scale reading, and if you see the sixth division of the vernier scale is coinciding. So therefore 6 multiplied by 0.06 6 multiplied by 0.01 centimeter, that is equal to 0.06 centimeter will be the reading from our vernier scale. Hence we have to add these two readings. So it will be 1.50 centimeter and plus 0.06 centimeter. So it totally comes out to be equal to 1.56 centimeter. Okay, now all these readings we have done in case when there is no zero error present. If there is a zero error present, initially we have to find out what is the zero error, and whatever may be, it is a positive or negative, whatever it may be, we have to subtract it from the final reading which we get. Okay, this simulation will directly do it, but you can try yourself different readings. Say just by making this virtual display values off, you can do all those readings yourself, and then you can try the different zero error values, etc. Okay, I hope that you understand this simulation. Thank you very much for your patience listening. Thank you.